In this chapter, we will learn about the sequential circuits. The sequencing requires the operation goes from one to the other. It has some sequencing element. The critical sequencing element is like a flip-flop, such as the memory. So it requires some history. So depending on the history or current state, you respond differently to the current input. So we will see what would be the sequencing element and how we designing. And we will also cover on the maximum and minimum delay, because the sequential element operate based on the clock, the periodic signal. In that case, you have the maximum operating speed limited by the clock frequency, and then it has the period, one clock period you have to complete. So the sequential circuit mostly based on the clock. So every clock rising edge or clock event, until the next clock event happen, you have to complete your operation, and then in the next cycle you do another job by taking new inputs. In that case, we have to care about maximum and minimum delay on the path, and also clock skew between this kind of sequencing elements. We will also talk about the time borrowing, how we move this maximum operating point. We can slightly move the operation calculation from this rising edge. Just we can delay that. In the next cycle, we will have a shorter logic operation time. So we can borrow the time from the next cycle or the other way. So we can also learn about the two-phase clocking that ensure that kind of give us very good margin on the setup and hold time, all kind of issues we will cover in this section. So sequencing is different from combinational logic. So combinational logic, whatever input changes, sequential logic, output changes. The output only determined by the input and an x and a y. That gives us the output. But the sequential logic, other than input, it also depends on the status, current status. If the current status, depending on the current status, for the same input, you will get the different output, right? Coming in and out. So it looks like a combination logic and the flip-flop memory block, right? You can spread the loop like this. It is the same thing. If there's any input coming in to the combination logic, the output determined by the input and some status coming from the flip-flop. That determines the output. So we have a finite state machine having a loop here, the pipeline structure. Without loop, you just pass through the data here. The pipeline is mostly used in the data path. Finite state machine mostly used in the control part. It's like a brain. So finite state machine actually control this kind of a pipeline stage on like a data path, right? There's a data path here, there's some brain here that control the sequential operation or sequencing or whatever the operation, right? It's like a brain, right? let's say we have some kind of a logic 1 and logic 2 and logic 3. Let me erase this. So if I have a logic 1, logic 1, logic 2, and logic 2 and logic 3, etc. Logic n. When the input comes in, then output comes out at the same time, x2 and x3, xn, y, xy, y, y2 comes in y3 and x3 and y3. If the input changes, all the intermediate node output comes out at the same time, and then final result you will get at the output as xn, yn. In that case, you don't need the sequential element like a flip-flop in between, because all the output arrives at the same time. But in reality, some of the paths will faster, some of the paths is slower. So output just at the output, in each stage output, the result will be very meshy. You don't know where to catch the data in the end, right? So that's why we put the sequential element like a flip-flop there. So by adding the sequential element in the middle, we launch the data on the next block at the clock rising edge at the same time, right? So we time the output of the logic so that we send out the output at the same time to the next combination logic. That's kind of called the sequencing. But if the logic propagation delay all the same, then we don't need this kind of flip-flop in the middle, because the data arrives at the same time. That is called the wave pipelining. Actually, wave is like a ripple. The data changes, ripple through the combinational logic, and then you will see at the output. But in reality, there's no such kind of we cannot guarantee such data arrival time is all the same. So we don't use wave pipelining. Instead, we use sequencing. So we add the sequential element. Only application currently where the wave pipelining is used is memory design. In Samsung memory, they are designing the very high-speed logic. They need very low latency. When the input changes, the output comes out very fast. So they design all the data paths and the same delay to have the same delay, so that they have a complicated operation at the very fast in the very short time. That's the only application. The wave pipelining technique, Samsung is the best in that technique. But as a commercial or popular design, the common block design for us, we use pipelining by adding the sequential element. So if you decided to make a sequencing like adding flip-flop between the combination logic, the overhead is the flip-flop, right? So such kind of flip-flop also adds some delay, right? So that you have to have some overhead to the logic operation. By adding the flip-flop, the overall computation is kind of slowed by the flip-flop. This is called some clocking overhead. By adding the clock, periodic clock, onto that, we get some overhead. This is a kind of a side effect of the maintaining sequence. So we have for the clock, if we have hundreds of thousands of flip-flop there, we also need to add a large of a buffer between them, so that we can drive the many flip-flop at the same time. So this is quite large overhead. The overall power consumption maybe comes from almost 30% of the power consumption uh, comes out of the clock tree buffer power. Let's take a look at the sequencing elements. We have two elements in this example, the latch and flip-flop. The latch is level sensitive, so as you already learned in the beginning of this lecture, so latch has a transparent mode and latching mode, right? Transparent and hold mode. Flip-flop is edge triggered. It can be either rising edge triggered or falling edge triggered. So we call it the flip-flop sometimes, master-slave flip-flop, because we implement the flip-flop by cascading master latch and slave latch. Or we say the D flip-flop or D register or whatever. The latch we draw like this, just latch black box, and clock comes in, data in, and data out, Q. Flip-flop we add like this kind of a notation to representing edge triggered operation. So in this example, the timing diagram, we show that the latch operation. So when the clock is 0, we hold the value. When the clock is high, it follow the input, it pass the input. So if the pass is input, it just follow the input, right? During the transparent mode. Right. Once the clock goes down, it hold mode happens, it just hold. Even though the input changes, it doesn't affect the output, right? And also when it goes up again, it transparent mode. We follow the input, right? But for the flip-flop, it behaves differently. So it only, for this kind of rising edge flip-flop, it only catches the data. So it catches data here, it goes to 0, and it catches data here, high, it go up here, something like that. So the latch behavior and flip-flop behaviors are different, so you have to understand properly. So what you have to also care about, you have to be aware of, is that for the flip-flop, the data comes out after a certain delay, that is clock to Q delay, C clock to Q, CLK2 Q, C to K. So this is C to K delay, C to Q delay. We have this amount of C to Q delay happen. There is a non-zero clock to Q delay. Latch also have some delay, right? So in the data path, we will have a little delay here to pass through the latch. So in this example, we draw, so again here, we draw some arrow signals. The arrow representation is very useful. This arrow is drawn only when it represents the cause and result, right? Cause and result. So it represents the causality. For example, for the rising edge flip-flop, by the action of the rising edge shown in here, that results in the output changes, right? Rising edge happen, the result in output edge changes. For the D latch, clock doesn't change. Clock rising edge can also, when it enter into hold mode and transparent mode, it follow the input, so this kind of a Gaussian result happen. And also when in the transparent mode, this is hold mode, transparent mode, the data changes, that also causes the output changes, right? This arrow shows the such causality. Okay. Let's design the simple latch. So we know that the basic latch has a transparent mode and hold mode. How we make it? So simple one pass transistor here, MOS here. So is this enough for latch operation? At the first look, it may work as we intended. For clock edge high, the switch is on, data passes to the Q. When the clock edge off, the switch is off. If there is a parasitic capacitor there, we may hold the output using parasitic. It can be like a dynamic logic. But this kind of implementation supposes the pros and cons, the advantage and disadvantage. The advantage is it's very tiny with low clock load, because the clock signal only go to the single device MOS, so it has a very low clock load. Actually, this kind of thing is used in 70s, but the problem is it has a VT drop for passing VDD, right? When you apply the VDD here, we want to charge onto the load capacitance, but by the current direction, this is gate and source, right? For that switch to be on, VGS need to be greater than VTH. So maximum voltage up until here is when the V is VDD, the source node will be VDD minus VTH. So there is a VTH drop for passing VDD. And also it's non-restoring, so the input voltage just delivered onto the output without restoring the logic level. And also backdriving, so there's no isolation, so any glitch on the output Q, that can be also passed on to the D, right? So the backdriving maybe happen. So output noise sensitivity is very bad, so it is like a floating capacitance, floating cap. So any the largest signal line nearby, if it may couple onto this parasitic capacitance, the value can be altered, right? It is a dynamic circuit because it relying on the floating capacitance, right? All the domino issues, the problem that domino circuit has is also presenting here. And the diffusion input, for the input is the diffusion capacitance rather than drain capacitance. So diffusion, for the gate capacitance, you are seeing CGS only. For the diffusion capacitance, you are seeing source capacitance and then drain capacitance like that, right? So you see more capacitance on the when you driving this kind of the switches. So To reduce the VTH voltage drop, we can use a transmission gate like this, NMOS and PMOS in parallel, like this. So there is no VTH drop, but it requires inverted clock signal. To resolve the restoring capability, we can add inverter so that the input data X is recovered by the either VDD or ground, right? You may have a choice of the adding buffer at the output or input. So here we have an inverting buffer added, so restoring, so no back driving, no reverse coupling, reverse isolation is better, right? So we can fix the output noise sensitivity, or we can reduce the diffusion input by adding the inverter at the input, right? But for the above, if we add a buffer at the output, then input parasitic capacitance diffusion, we have a PMOS, NMOS diffusion capacitance that there. So for reducing input capacitance, we would better add inverter at the input. Problem with this, for this kind of latch, since the inverter is just single stage, the output is inverted. No matter what the inverter is at the input and output, we know that in the previous example, it were like relying on still the parasitic capacitance. So this parasitic sensitivity, the external noise and leakage. So to avoid that, so during hold mode, we add this kind of a tri-state buffer. That is 2, 3, 4. CK, this is a phi, when the phi bar there, it activated phi there. So when the phi is low during hold mode, activate this inverter, tri-state buffer, so that the structure becomes the latch. So transparent mode, it looks like this. Hold mode, it constructs like a back-to-back inverter structure, right? So that we can remove the parasitic effect. So in this implementation, we can ensure that all the internal nodes are driven any mode, right? So it becomes just static logic. But by having this kind of backward logic added, there's some risk of a backdriving risk. Any glitches on there, the output will pass on to the input. But this one will be the non-issue when we have a large noise margin there. Solve that by having noise margin. So now this kind of implementation is a very essential structure, that having static latches. So having static latch So during hold mode, it gets like this kind of a back-to-back inverter state, right? Hold. This is very important for the latching design. To reduce the input diffusion capacitance at the input, we can add additional inverter at the input, right? So fixes the diffusion input, and it becomes now non-inverting by having two inverter in the path. Another thing is buffer the output. So if you use this latch and driving long line, the timing that driving this kind of a latching core might affected by the loading capacitance. If you have a large capacitance, this latching timing will be slow, something kind of like that. So the latching core sensitive to the loading. So to reduce this such effect, we add additional buffer there, like this. Then no matter what the upload is, the latching core timing or behavior will not be affected by that load. So buffer the output there, so no backdriving issue. This kind of actual structure is widely used and very robust. But we have many input and devices, many the devices, inverter and flip-flop. Right? For this kind of single latch, this is a single latch implementation. Is good for this, right? To reduce the output loading effect, you may add a buffer like that, adding another inverter there, but then you get the inverted output, right? Then you may have to have an additional inverter there, right? So that the output loading doesn't affect the latching effect, right? But if you have an inverter there, you may have you don't have to add a two inverter there. So this one have a high clock loading because many devices here loaded by the clock. It is quite slow implementation, but very robust. You can simplify the latch design by eliminating input inverter there, latch timing, but you get the inverted output. It becomes smaller and faster, but input is unbuffered. So this timing, the data, the edge behavior, also in this implementation also is very sensitive to input loading condition or input driving strength that affect the waveform on the X. So it is very sensitive. The behavior is very sensitive, similar to output load variation. So without buffering, this kind of a driving buffer state or wire capacitance affect the behavior of this latch design. So this is not good in general. Actual implementation, we can have a flip-flop back-to-back latch there. This implementation relying on the dynamic parasitic capacitance. This is dynamic flip-flop, we can say that. So this parasitic capacitance holds the value, but this is very sensitive to noise. And also leakage and leakage. This kind of a flip-flop only works in very fast operation, so that the clock frequency must be fast. For low clock frequency, this kind of a dynamic flip-flop will not work because of the leakage. The voltage will be leaked out. So we prefer to have a fully static implementation shown here. We have a first latch here. We have a second latch. In this example, input we have the inverter there. In the second latch, we didn't put the inverter because we already inside this latch we have inverter in the previous stage, and they're tightly placed, and there's no unknown parasitic or input. The wire capacitance is very well controlled, so we can remove the inverter, and then we put another inverter there to ensure that polarity. For Q bar, we add the inverter into here like that. So from this structure, we see that input is buffered and output is also buffered, so that the input condition and an output condition will have a less effect on the actual operation of this kind of flip-flop. Okay. For flip-flop implementation, we can add enable control for the flip-flop, so that when the enable is 0, we don't catch the value. We just ignore the clock edge. So we hold the value for the enable 0 without taking new data input. So by adding enable or load signal can be implemented with the multiplexer here at the input. So when the enable happen, only passes on to the latch or flip-flop here, right? So we can add multiplexer. But this one increase the latch D to Q delay, right? Data Q delay by adding multiplexer in the path. The other way is you can gate the clock by when the only enable is there, then we can pass the clock there like this. This one will increase the setup time and clock skew because the clock will arrive a little later, right? So the clock is like slightly delayed by that and gating, right? Circuit. All these things need to be taken care of by the tool. And also, we have this kind of implementation has the glitch issue, clock glitch issue. For example, when the clock is coming in, enable and disable enable signal happen like that. Output clock will be like this, right? This kind of a clock glitch, very short, narrow clock pulse, will make the flip-flop behave wrong. So we must avoid that. Typically, for when you gate the clock, we implement using this kind of core, the latch core, so that the enable signal happen only clock goes low by adding the latch there. So we latch here, active low latch, and here enable signal that goes to clock gating circuit. clock gating like that. So enable only passes on to when the clock is low, then this clock enable signal will be activated at that time, right? When the clock goes low, then the output will be cleanly generated, the output clock, with no glitches. So this kind of a gating clock cell must be available if you want to do nicely gate the clock. For reset signal, you want to disable the output and also internal latch. You want to force the output when reset is asserted. There are two ways to implement is the synchronous reset and asynchronous reset. This concept is very important. For synchronous reset is a reset, actual reset happens when the clock edge passes. So during this synchronous reset, actual reset of this latching core will happen when clock is high, right? Like this, right? This, if you do the actual reset at the input reset gating, you put the reset gating in front of the latch or flip-flop, you can make a synchronous reset. So when the clock comes in, CK output Q was high, the reset signal comes in anytime like that. When the reset goes up like that, the output Q will reset only, let's say flip-flop, let's say Q, let's say flip-flop output will reset at the time next rising edge happen, right? This is quotient result, causality like that. For the latch here, the reset happen when the clock is high, right? So clock is high, so reset output coming in when the clock is this here. Reset goes down like that, right? This is a different behavior for the latch and flip-flop. But if you do the asynchronous reset, it reset the internal core SR latch here for the flip-flop, and also latch is also here. So the output, the reset will happen at the very moment of the reset signal is asserted. So in the previous flip-flop case, when the reset asserted, the output goes immediately down for the asynchronous reset. For the latch, in this example, it's both asynchronous and synchronous reset happen at the same time. But for example, if you have a different waveform like this, so clock and reset, let's say reset happen like there, output Q latch output for asynchronous. If you look at the latch output, when does it reset? For the synchronous, the output latch goes down at the clock rising edge. But for asynchronous reset, when the reset happens immediately, it goes down. This is asynchronous, async. This is a sync reset, right? So both synchronous and asynchronous reset you have to be very careful for designing reset. For asynchronous reset, you must reset internal core as well, right? This is very important. Students neglect to reset the internal core for implementing a synchronous reset. For power on reset or whatever, most of the reset implemented in asynchronously, so that ensure internal memory all the flushed out and cleanly reset. So important. This flip-flop, it has the flip-flop has the capability of the set and reset both. We can set the flip-flop to high or reset to 0. As you can see, the set and reset control signal inside this SL latch loop, the latching core loop, so that we can do that asynchronously. So this is asynchronous set and reset. So when same hardware flip-flop, you can have both set and reset, right? This is very useful implementation. When you have this, you can do various things you can think of.